Hi, everyone, and welcome back. It's Kira Garfolo with Greenville Tech's Math 109. Today, we're going to jump into Chapter 4, and we're going to start with Section 4.1, which is Transformations in Graphs and Symmetry. So before we dive into this material, though, I want to give you a bit of a warning. Not to scare you away, but on the contrary, to encourage you. In this section, we're going to talk about all the different ways we can move and manipulate the graph of a parent function. And a parent function is just a fancy way to say that we're moving and manipulating a graph that had an original simple function, right? Like y equals x squared. We know that that's a parabola that starts at the origin, or y equals x, or y equals the absolute value of x. We're talking about basic underlying functions. If you remember in a previous section, we talked about some of the famous power functions that you maybe want to be familiar with. And that's kind of what we're going to see here. So now with the caution, this is a heavy section. There's a lot of information thrown together into this section. So pace yourself. This is a recording. Pause it, walk away for a little bit. Watch it all and then come back and watch it again if you need to, or skim through. However you need to manage this, that's fine. It is a lot of information, so handle it how you need to. You'll need to review, and practice. I know I say that at the end of every presentation, but really with this one, it's really kind of, there's some memorization involved, there's some learning the rules, and the only way that you're going to master those rules is really to get some practice. Not anything that we're doing today is particularly hard or difficult, but it's also just, it's a lot and it can be overwhelming. So if you find yourself overwhelmed to the point that you can't pay attention, take a deep breath, walk away, and come back. Let's get started. So the simplest thing, in my opinion, that we can do to a graph is to shift it. So basically that means we're going to slide it side to side, or we're going to slide the whole thing up or down. In a vertical shift, the graph is going to move up or it's going to move down. So it's going to move vertically. We do that in our equation by taking f of x and adding a number. K here is just any number. It could be 1, it could be 5, it could be 5 million. So we have our original function, our parent function here, f of x, and we add k. F of x minus k is going to move it down. So plus is going to go up, minus is going to go down. That makes perfect sense. Now, on the other hand, we have something called a horizontal shift. Excuse me. And a horizontal shift is going to move the graph horizontally. You guessed it, left or right. Now, when we do this, we change what's inside the function, okay? So now instead of just adding or subtracting k after the function, we are actually building in f of x plus c or f of x minus c into our function. So like we did with difference quotients, anywhere you see an x, you would put a plus c or a minus c. Now this one's a little bit tricky too. If we add c within those parentheses, we are moving the graph to the left, okay? I know that we are adding, so it may seem that you would move upward. You don't, you are actually moving backwards. F of x minus c is going to move it to the right. There are many ways to try to make sense of this. Personally, I just remember that it's the opposite. But if you think about it, I know I've had students in the past say, okay, well, if I move it to the left 3, so from 0, 0, I move it to -3, 0, then I would have to add 3 to get it back. So the adding is what shifts it to that left. However it makes sense to you, or whether you just, grin and bear it and memorize it, just know that f of x plus c is going to move it to the left, and f of x minus c is going to move it to the right. As we'll see, it's kind of a common theme throughout. If you're ever in doubt which way it's going to go, just test a point, test a couple points. You always have an option here to test some points. Now you can apply these on their own. So maybe you just take the graph and you move it up, or you move it down, or you move it left, or you move it right. But you can also apply them simultaneously. Let's look at a couple of examples. Before we dive into the examples, I forgot about this bullet, I'm sorry. Shifts are what I call them and often what your text will call them, but in some other resources, you may see them called translations. You're just translating or sliding that graph up and down and left and right. So let's look at some examples now. Our original is in red here. This red right here is y equals x squared. So it's just our standard parabola, 0, 0, 1, 1, negative 1, 1, and so on. You could plug a lot of points into here, okay? If we have this black dotted line, we have y equals x squared plus 3. So notice here that this plus 3 right here is outside the original function, so it's just going to shift it up 3. In the green, we have over here y equals x plus 2 quantity squared. So that plus 2 is in with the function, and plus 2 is going to move us to the left. So the shape stays identical, it just shifts over to the left. And if we wanted to apply a couple of different shifts at a time, we could have this blue one, a y equals x minus 4 quantity squared minus 1. Doesn't matter which order you do these in, you're going to get to the same place. So you're going to drop that x squared down, and you're going to move it over to the right 4. Minus 4 goes to the right 4. You could go to the right and down first, it doesn't matter. So these are all what we call translations or shifts. Take a few moments and make sure that you can make these make sense, because they are the simplest of the cases that we're going to see. Now, in addition to just moving things up and down and side to side, we can also flip it. Okay, we can maintain the identical shape, but we're going to flip it over one of our axes. If we want to reflect it over that vertical y-axis, we're going to find f of negative x. So anywhere in that original function that you see x, you're going to plug in a negative x, and that'll give you your new function to graph flipped across the y-axis. If we want to reflect it over the horizontal x-axis, we're going to use negative f of x. So we're going to take that entire original function and we're going to multiply the entire function by negative 1. Let's look at an example. Here in the red solid line, we have our parent function of absolute value of x. Remember, absolute value symbolically is the vertical bars. So you have absolute value of x here in red, and if we want to reflect it across the y-axis, across the x-axis, the horizontal x-axis here, so we're going to just plop it down, we do a negative times the entire function. So negative absolute value of x is going to flip it over there, and we see a mirror image with the mirror being this horizontal axis. Now, if you take a minute and think about this, flipping the absolute value parent function, so flipping this red v that we see across the y, won't give us any change. Because the absolute value of negative x, remember flipping across the y, is going to give us that flip across, right? We're going to have a negative x anywhere we had an x. That is going to give us the exact same answer because the absolute value of 3 and the absolute value of negative 3 are the same thing. They're just 3. So take a few moments, practice that, make sure it makes sense, and then you can move on. Here's another example of reflecting, and in this case, this is not one function flipping across the y. Remember, it wouldn't be a function because it doesn't meet our vertical line test. Instead, it's just this little blue piece right here in the first quadrant that is y equals the square root of x. Okay, so that's our square root parent function. Y equals square root of x is right here in that first quadrant. If we wanted to flip it across, so we want to reflect it across the x-axis, across that horizontal axis, then we are going to make negative f of x. So negative square root of x. That's going to give us this yellowish brown here. That's going to give us the flip across the x. Instead, if we wanted to start here at our original and flip it across the y-axis, then we would do negative f of x. So we would do, we would do negative x, f of negative x. So we would do the square root of negative x. So we're going to flip it by doing the square root of negative x. And remember, a square root of a negative number isn't defined on the real number scale. So since it's not defined over here, Negative of a negative is positive. Negative of a positive is negative. So this is why it flips directly over here. Square root of negative negative 4 is just the square root of 4, which is 2, which is this point right here. Now we can also combine these and do both. We could do the negative square root of negative x. And that is going to allow us here, we're going to flop down across the x and flop over across the y. You could do those in either order also. You could flop over the y and then flop over the x. Either way, you can combine and you can start flipping things all over to get the graph you need. Now, everything we've talked about so far has maintained the exact same shape of the graph, okay? So we've maintained the shape of the graph, we've just moved it around. Maybe we've flipped it over, we've taken a mirror image of it, we've split it up, we've slid it down, we've slid it left, we've slid it right. But we can also change the graph by vertically shrinking it or stretching it, okay? The primary shape is maintained, so if it was a parabola to begin with, it's still going to stay a parabola. But now it doesn't remain identical. It may stretch up and be taller and more narrow, or it may compress down and be flatter and not rise as fast. So that same basic shape is maintained, but it does change a little bit in the scale. Now, vertical stretch occurs when we have our function multiplied by a constant c, where that c is greater than 1, okay? So we're multiplying our entire function by some number greater than 1. And I like to think of vertical stretch as if you put your arms out like a V, like the absolute value, and then if you pull your arms up like you're stretching, like you're yawning and stretching, that's a vertical stretch. The graph is increasing more quickly, and it's becoming taller and narrower faster. On the other hand, we can have a vertical shrink or a vertical compression. Those can be used interchangeably. You'll probably hear me interchange them. And that occurs when you have c times the f of x, or some number times f of x again, but that number is between 0 and 1. So you're multiplying it by a less than 1 positive number. So you can think about flattening out or stooping down. If you think about a snowman melting, the same shape is kind of maintained, but it's fatter and you're not as tall quickly, and it just kind of plops down and is more of a blob. So vertical stretch is when we get real tall real fast and reach up, and a vertical shrink is when we push down. If you think of, one of my students talked about a marshmallow, right? If you're vertically shrinking it, you take that marshmallow and you stretch it out. And if you're vertically shrinking it, you take that marshmallow and you push it down, and it kind of flattens out. This is a lot more fun in person because I always make a fool of myself stretching and shrinking and sliding one way or the other. And you can imagine that it's kind of an interesting little lecture. Let's look at an example because I know that examples help a lot. Let's talk about the parent function f of x equals x squared. So f of x equals x squared is this, I know it's a little difficult to see, but it's this x squared is red right here. It's that middle parabola, okay? If we have f of x equals 2x squared, we're multiplying our entire function by 2, which is greater than 1, so we're going to have a vertical stretch. That's going to give us this top blue one right here, and you can see that it gets taller faster and it's a little narrower because it's stretching up vertically. If we have f of x equals 1/3 times x squared, 1/3 is between 0 and 1, so we're taking it from this red nice shape and we're flattening it down. It's still a basic parabola, but it's fatter and it's opening more slowly. It's not reaching up, instead it's kind of falling down. Now this is all a lot of information, right? This would maybe be a good time to take a break, maybe summarize some things, summarize the rules so far and put them on some note cards, write them down, whatever you need to do. Again, you can pause and walk away whenever you need. But we can also put all of these rules together and get extra practice. And we can start that by this example where I'm going to give you the parent function. I'm going to tell you what we want to move it around to, and you're going to tell me what the function will be defined as. So these are great that if you want to get some practice, when we talk about what we're going to do, you pause it, you work it yourself, and you see if you get the same answer that I did. So for this first example, we're going to shift the graph of y equals x squared. So we're going to shift that parabola 2 units to the right and 1 unit down, and then we're going to reflect it across the x-axis, okay? So I'm going to list these in a series of different functions. And that function, just to describe some notation, this little subscript here is going to say, okay, if it's f of 1, it's going to be the first transformation I apply. If it's f of 2, it's the second one I apply, and so on. It's just to keep some notation straight. And when we get our last one, that'll be our final answer. So the first thing we need to do is where we start is y equals, or f of x equals x squared. And we need to move it 2 units to the right. So we started at f of x equals x squared. 2 units to the right, remember, it's going to be x minus 2 squared. So remember, we're just going to add this minus 2 within those parentheses. Anywhere we saw an x, we need to put an x minus 2. Again, I understand that this can be an intuitive little bit of a nightmare here, that having x minus 2 here is kind of counterintuitive in that minus 2 is going to the right, but it is. When we're done with that, we also need to shift it 1 unit down. So when we shift something 1 unit vertically, we shift something vertically at all, that comes after the entire function. So we're going to take what we already have with x minus 2 squared, and afterwards we're going to tag on a minus 1 because we want that whole graph to shift down 1. And lastly, we want to reflect it across the x-axis. So when we reflect it across the x, we're reflecting against horizontally, and that means we need to multiply the entire function by -1. So we're going to have negative everything we just saw. So negative x minus 2 squared minus 1. Now you can distribute this negative. That will give you negative x minus 2 squared plus 1. You could FOIL this out and get an entire quadratic. You can do this several different ways. Here's the fully simplified version that you'll find in the departmental notes. You could work it out to be negative x squared minus 4x plus 4 minus 1, which is going to simplify to be negative x squared plus 4x minus 3. Generally speaking, your homework's going to tell you exactly what format it wants it in. And as far as I go, if I don't tell you standard form or I don't tell you any certain form, as long as it's mathematically correct, I won't be expecting simplification. It's a good idea to graph your example. If you have a few moments, you can graph it on your calculator. These graphs that I've used today are on the Desmos online calculator. It's a little easier to show than the on-screen calculator. But it's a good idea to graph and see the transformation to check your answer. Again, you're only going to have your calculator on your test, so it's probably a good idea to practice there. But it's just not as pretty for illustrative purposes. It's great to check an answer. It's kind of rough. Can't do the colors and things like that. So I choose to use Desmos for my PowerPoint. But you can see here that our original was x squared. And what we ended up with here was y equals negative x squared plus 4x minus 3. So remember that the first thing we did was shift it 2 units to the right. So we had x minus 2, right? And then we shifted it down 1 unit. So we'd still have a parabola that looked like this with a vertex right here. And then we flipped it over that horizontal axis. So that's what flipped it upside down and then effectively brought it up. Because we're flipping it right here. Here's another example, and I want you to give it a try. We want to shift the graph of f of x equals the square root of x. So we're going to use the square root of x as our parent function, 2 units to the left, and then we're going to reflect it across the y-axis. And lastly, we're going to vertically stretch it by a factor of 2. So pause the video, take a few moments, and give it a try. When you're ready to proceed, let's see if you can get the same answer that I do. We're going to start here by starting with f of x equals the square root of x. Shifting it left by 2, you're going to put anything where x was, you're going to have x plus 2. Remember that that plus moves us left. So now we have the square root of x plus 2. To reflect it across the y-axis, anywhere that we see an x, we have to put in negative x. So we end up with square root of negative x plus 2, or equivalently square root of 2 minus x if you don't like that minus being there. And lastly, we want to vertically stretch it by a factor of 2, which means all we need to do is multiply that entire function by a factor of 2. So we're left with 2 square root of negative x plus 2, which gives us this blue line. You can look here and see that it's vertically stretching because it's getting taller faster. You can see that it has been reflected because now it opens that way instead of that way. And I know that it looks like it shifted to the right, but it actually shifted to the left because we started here and then flipped it over. So that's just one thing that you have to be careful about. We can also work backwards. If we're given a function, and I tell you the parent function, we can describe the transformations to that parent function that would result in the given function. So now we're just going to be working in the opposite direction. Let's look at an example. Before we dive into the example, this is a very important word of advice. When you're working backwards, it's a good idea to list your stretches and your compressions and your reflections first. Then list all of your translations and shifts. So do your coefficients out in the front first, and then you list your translations and shifts. Let's look at an example. Find the parent function and the sequence of transformations that leads to this function. Then we're going to graph the function and take a look. So g of x equals negative 2 times x minus 3 cubed minus 2. So where do we want to start? Remember that we want to start with reflections and we want to start with shrinking and stretching. You can put either of those and you can put those in either order, just like you can put vertical and horizontal shifts in either order. It's not going to affect anything. But we definitely want to start with shrinks, stretches, and reflections. So here we see that we have a negative 2 out front. But first, what did it start as? We see a cubed here. So we say, well, it probably started as x cubed. So that's our parent function. We see that there's a 2 out here. So it's vertically stretched by a factor of 2, and that would give us 2x cubed. But we also see that negative there. And the negative is going to be a reflection. The negative out front and not attached to x is going to be a reflection across the y-axis, remember. So that was going to give us negative 2x cubed. So listing the transformations, we see that we have a vertical stretch by 2. We're reflecting across the y-axis. Then we can talk about our shifts. We know that we shifted 3 to the right because we subtracted 3 here. Remember that to the right is a minus. And then from this negative 2, we know that we went down 2 units. So it's kind of like a puzzle. Again, these two could be in either order and these two could be in either order, but you definitely want these two to be first and these two to be last. If you caught me when I was speaking, I actually was going to mention the reflection before I mentioned the stretch because I tend to look at the negatives first. But clearly when I made these notes, I was thinking the otherwise, or perhaps the book went. Anyway, take some practice, pause this, repeat this if you need to, because this is a great practice problem. We're going to do more examples too. If we wanted to graph this, we can see it. Our original function is this dotted green line. It's the cubic function. And our new function is this solid purple blue line, okay? So we can see that we moved down 2 units, that we shifted to the right. Oh my gosh, my mouse is freezing. Okay. And that we reflected. So we moved down 2 units and we reflected. Now I want you to pause this video and give this one a try. I want you to list the parent function and the sequence of transformations that led to the function. When you're ready, you can move on and see the solution. So we start with 2 times the absolute value of t plus 2 plus 3. So it doesn't take too much to realize that our parent function is going to be the absolute value of t here. Okay, so that's going to be our parent. We see this factor of 2 out here, so we know that's a vertical stretch by a factor of 2. We don't see any negatives, so that's good. But we also see that there is going to be a shift here and a shift here. So we know that the t plus 2 is going to shift us 2 units to the left, and that this plus 3 is going to shift us 3 units up. So you can see all of these answers right here. Now, we can also work from a graph rather than a given function. This can be a little bit trickier with stretches and compressions. It's not impossible by any means, as we'll see here with this example, but I highly encourage you to use test points, at least 1 or 2, to make sure that your answers are right. Really, you can use those all the way out throughout everything we've talked about. If you're building a function or if you're listing transformations, plug in a couple of x, y values and make sure that it's what you think it should be. So in this example, it certainly looks that v shape, the only function that we really work with that's a v like that is our absolute value of x. So this certainly looks like an absolute value of x. Now let's just talk before we move on about some of the things that have changed about that. If you look, it looks like it's certainly moved down, right? Because absolute value should be up here. Absolute value itself can't be negative. So obviously we have a vertical shift going on. It doesn't look like it's flipped anywhere because it's still an upward opening V. But it does look a little tight, right? It looks like it's reaching up a little narrower, a little faster. So we must have some sort of vertical stretch. Now, the vertical stretch is, like I said, the tricky part to nail down. So you see this has shifted down by 1, 2, 3, okay? If this had moved up 3, then this value would be -2, 6. This is how I would find the value of that stretch. The absolute value of -2 should be 2, but instead we have -2, 6. So that is going to be a factor of 3 that's going to be applied. So use the point that you're given to make sure that you're getting the right factor. So we see that it's a vertical stretch by a factor of 3. Again, use test points to be certain on those factors. Like I said, that -2, 3, before we dropped everything down 3 units, it would be -2, 6. And so absolute value of 2 is 2 times 3 is going to give us that 6. And then again, we have that vertical shift down. So our answer is going to be 3 absolute value of x minus 3. Always, always, always plug in a point to check this one, especially that -2, 3 here. It's given as a point. Plug it into your new function. So 3 absolute value of x is going to be 3 times absolute value of 2, which is going to be 6. Minus 3 is going to give us 3. So our point -2, 3 does indeed work. It's always, always a good idea to plug that point in. Okay. Now I want you to pause the video again and take some more practice. You want to find f of x given the following graph. So here we can see that it looks to me like a square root function, right? But obviously square root comes over here, so it's obviously flipped over. And we can also see that since 1, 1 would be right here, that we have some sort of smooshing down, okay? So we have some sort of compression going on. It's still starting at the origin, so there's no big deal there as far as a shift goes, but it certainly is having some sort of vertical shrink. So again, we're going to reflect it across that y-axis. So anywhere that we see an x, it's going to be a -x. So that'll give us a square root of -x. And then we see that it's vertically compressed, and we can figure out that it's by a factor of 1/3. So our final answer is 1/3 square root of -x. So again, you might have to use a couple points here to make that make sense. I always like to look for points that look relatively exact. So I would go over here and say, okay, well, -9 hits 1. I know that the square root of 9 is 3, so that 1/3 has to come into play because I'd have to multiply 3 times 1/3 to get to that 1, that it would make sense here. And it can be a little bit of trial and error if you're kind of looking at a graph blindly and guessing, but it's not too bad. Let's talk about one more thing. I told you guys this was a heavy section, huh? So we're going to talk about even and odd functions. And this plays into the symmetry in the title of the section. So a function is even if for every x in the domain, the f of negative x is equal to the f of x. So that means that anywhere you see an x in your original function, if you plug negative x in, and when you simplify that, you get the exact same function that you started with, that is called an even function. And it can be shown that that is symmetric about the y-axis. Remember that we plug a negative x in if we're wanting to flip it across the y-axis. So it makes sense that if it's exactly the same on the left as it is on the right, mirror imaged, that this would give us, it could flip across and be the exact same, right? It could reflect across and be the same. So those are not unrelated to what we talked about earlier. This is an example of an even function because you see that right here, if you use this as a mirror or you folded the graph over on itself right here, it's perfectly symmetric on the left as it is to the right. On the other hand, a function is odd if for every x in the domain, f of negative x gives us negative f of x. So in both cases, you're plugging f of negative x in. It just matters what it becomes as to whether it's even or odd or neither. If when you find f of negative x, you get the same exact function you started with, it's even. If you get the negative version of the function you started with, the whole function that is, that's going to give you odd. And if you don't get either of those, then it's neither even nor odd. And that's a very common thing with functions. Don't panic if it's not even or odd. It could be neither. So odd functions happen to be symmetric about the origin. And this is really hard for me to visualize. I'm sure I'm not alone here. You can think of a mirror across the origin, or think about rotating that graph 180 degrees about the origin. So you would rotate this piece up here and then over 90 more degrees. And so you can see that it would be that 180 degree rotation, and it would give you the same. If you rotated this piece right here 180 degrees, it would lay right on top of this piece here, and vice versa. So again, to algebraically tell if it's even or odd, find f of negative x. Let's look at a couple of examples. We want to know if these are even, odd, or neither. So f of x equals negative x to the fifth plus 7x. Take a moment to pause and find f of negative x. F of negative x is going to be negative times negative x to the fifth plus 7 times negative x. This is going to come out to be x to the fifth minus 7x. Now notice this is definitely not the same one that we started with, so it's not even, because x to the fifth minus 7x is not the same as negative x to the fifth plus 7x. However, it is the same as the negative f of x. If we multiplied this whole, if we multiplied this whole thing by -1 here, we would get this answer. So that means that this function is odd. Now, what about this example? G of t equals t squared plus 6. Take a moment and find g of negative t and see what you find. Finding g of negative t, we have negative t squared plus 6. Remember that if you have a negative number and you're squaring it, that it stays, that it becomes positive. So negative t quantity squared plus 6 is still going to give us t squared plus 6. This is identical to our original function. So we have an even function. We could check these with graphs. Sometimes that's more convenient than other times. But looking at our earlier examples, we see that this is our odd function. So if you rotated this 180 degrees, you'd be on this side. And this is our even function. You can see that it's symmetric about y. So this one's odd, it's symmetric about the origin. This one's even and it's symmetric about y. If we folded it in half vertically, it'd lay on top of itself. Now, one thing to be careful about just using the graphs is that I find it hard to conceptualize and visualize odd on its own, but sometimes it could look like it's symmetric, but it's not perfectly symmetric. So you want to be careful, and if you can, algebraically check it out. Now you give this one a try. Pause your video and find out if this one's even, odd, or neither. You want to start by finding f of negative x. When you find f of negative x, you're going to get 2 times negative x plus 3, which is going to give us negative 2x plus 3. This is not the same as our original, and it's also not the same as multiplying this whole thing by negative, right? Because multiplying the whole thing, I'd get negative 2x minus 3. So now we know this one's not even and it's not odd, so it must be neither. Now I know your brains are tired after this entire lecture, but let's think for a second. Is there any function that could be both even and odd? That is there anything that I could draw, any function that would reflect across the y and also be symmetric across the origin? From an algebraic standpoint, I would have to have f of negative x is equal to f of x and equal to negative f of x. That thought is a little more concrete. Is there any number that the positive of that number and the negative of that number are the same? The only number that's equal to its own negative is 0. So that means that the only function that is both even and odd is going to be f of x equals 0. So that horizontal line basically laying on top of the x-axis. I don't know about you guys, but that made my brain hurt a little bit. One of our longer lectures for sure, so I hope you took some breaks, and I hope that you'll come back and watch it again to pick up whatever you've missed. Taking good notes is certainly fundamental here. So there's a lot of content here, and there are a lot of rules that need memorization, and there are a lot of rules that need practice, okay? However you make them make sense to you will work for you. As long as it's mathematically correct, you do you. Practice, practice, practice. There are lots of resources online in Blackboard. Use those departmental notes. Go to the Math Center if you're really struggling. You can drop by my office hours at any time if you're struggling. Any of those resources available, take full advantage of them. This is something that you will see throughout the remainder of our course. It'll keep popping up, and it's definitely something you'll see on your test. So make sure that you're proficient with it and make sure you give it some work. As always, if you have any questions, you know where to reach me. Thanks again for listening, and I hope to see you next time.